right, how's it going, everyone? Hope you're all doing well. So you've made it to the last earthquake lab. So if you weren't feeling the earthquake section, you're almost there. Okay, lab 4. So in this lab, we're going to be looking at only the P waves. So those are those primary waves that come first. And so even though they come first, they still will vary in speed depending on what like surface they're traveling through. Things will travel differently through the air versus the ground. Just think of sound waves as a good example. And so the two main types of waves we're looking at for this one are those direct waves, the P direct waves, and the P reflective waves. So these waves won't always take a direct path. A direct path would be, say, if we had an earthquake on the surface, it just travels through the surface and then hits the station directly. But some of them are going to actually go down, reflect down, and then if they hit a reflecting boundary, probably something like harder rock, they might not be able to get through and they'll just bounce back up. So think of like an echo, for instance. Why sometimes you can hear an echo, it's because it's bouncing around and hitting off the surfaces and coming back to our ears. Kind of the similar idea. So that PD would be a direct path, and the reflective would obviously take a little longer since it has to get down and come back up. So that's why it's got a lag to it. And so on figure 1 here, what we're looking at, there was a type of explosion just to create some seismic waves to give us some data so we could find the velocity of these waves. And along the surface, this top line is this Earth's surface. We have things called geophones, which help pick up the seismic data and spit it out into these nice graphs for us. And with this data, we're going to be able to determine where this reflecting boundary is. So you'll have to draw a line at depth somewhere where this boundary is. And I'll explain how to do that. And then when I was an undergrad, we actually did a lab like this. So sorry for the vertical pictures here, but I thought it'd be cool to show you kind of what you're working with. So we have all these wires. Each one of these little orange things are a geophone, and they are all tied and attached to this computer, which will spit out a graph like this. That's pretty cool. And so sometimes people will create a little explosion to create seismic waves. We were just hitting a block. We were just hitting a block with a hammer to give us data, and it works fine. So I don't know. I think it's kind of cool to see what you're working with. Yep. So that was the surface here. We would have geophones all along there, and they'd spit out the data. Okay. So for filling out this table, this is a lot of the questions in the lab. And it gives a nice description right before the table and just how to fill it all out. But I'll run through it. So looking for the direct path length, that's looking for how far each geophone is from the explosion. So geophone 1 is 200 meters, geophone 2 is 400 meters, and so on. The elapsed time for PD, that P wave direct time, we get that from figure 2, just wherever it peaks, and just try to be as exact as you can. Each one of these gaps is 0.1 seconds, so these things are going really quick. So just eyeballing it here, that first PD looks like it's at 0.09, I guess. I'm not misspeaking. Okay. And then next we could find the seismic velocity because we have a distance and a time. So we can just divide that direct path by that elapsed time and we'll get velocity. We can do that for all 8 and then we can find the average velocity from those 8 velocities we would have found. And then you're going to want to find the elapsed time for PR, PR being that reflective wave that comes afterwards, the one that bounced in the ground and came back up. And it'll be a little slower since it has a longer path to travel. It'll take more time to get there. And then we can find the reflected path length. So that was just the time. If we want to figure out at what depth that reflective boundary is, we need to get a length from it. And we get that length by multiplying that average velocity by that PR time. So units would cancel and would just leave us with meters. That's what that's doing. And then we're going to also want the half reflected path length, which you can just get by dividing that path length by 2. Okay, so the next part's going to have you sketch on figure 1 where that reflective boundary is and how the waves are bouncing back. So I have a little sketch here. Here's our little explosion, and then I just set up geophone 1 as an example. So here's the ground, here's the reflective boundary at some unknown depth that we need to find. So the waves, if we can think about it, our direct wave would go across the surface and hit station 1 directly. The PR would bounce down and up and hit it from below. And that would create a triangle. So how do we find how deep that reflective boundary is from this? Well, there's 2 ways you can do it. So yeah, we're trying to find depth. You can either use the Pythagorean theorem, since with this we have a triangle, so we have everything we would need. PD for station 1 would have been 200 meters. So for half that triangle, I just split that in half for 100 meters here. And this is why we found the half reflected path length, because that full reflective path length was this side plus this side. So that's not really helpful to us. But with that half reflected length, we have this side, we have this side, and we could find depth with a squared plus b squared equals c squared. So I did a sample calculation just to kind of show how it's going. PD would be 100. I did a PR half length of 450 as an example, and kind of just plug and chug, and that can give you depth. And you should more or less be finding the same depth for all of them. They might vary a little bit. It kind of just depends. If you don't like doing the math way, you can also, just since you already have the reflected path length, and we would know that each one of these is a half, we would know how deep it has to be anyway, but you'd still have to kind of get a ruler and measure it out. And I know that can be kind of annoying on screens as well. So whichever one works for you to find that reflective boundary. And we'd want to do that for all of them. And you'd get something that looks like this, but for all 8 of them. So you'd have the direct line at the top, the direct P wave, and then the reflective P wave would come down and bounce up, with that corner being halfway each time. And that's the figure that it's looking for at whatever depth you found doing the calculations. Okay. So the next part is doing the same thing, but maybe a little more confusing because this is a real life example. So it looks like a lot of data. We're only concerned with PD and PR. All of this other stuff is probably more reflective waves, maybe S and surface waves, and I don't know what else, but we only are concerned with PD and PR as it's labeled. And then one thing to note with this is the blast here did not start at 0. This one starts at 0.355 seconds. So just whatever that you find, don't forget to add 0.355 seconds. A little mean. And then we have another diagram here showing where each station is on the surface, and then we can plot and find the reflective boundary as well. You only need to do this for the even numbers. There's 12 stations, you only need to do the even numbers. And then also just be careful because the blast is here. It starts at station 12 and goes down, while the other example started at 1 and went up. And then, yes, I made a note that that reflective boundary for this might not be a perfect straight line. It'll probably be close, but since this is a real life example, we can't always expect the rocks to be perfectly straight. They might be kind of bent. So that's all right. And yeah, that's what I have for you. And then please let me know if you have any questions.